welcome to this course on noise control in mechanical systems with myself, Professor Sneha Singh from IIT Roorkee. So, we have been discussing about some case studies on noise control in mechanical systems, which is the last module of this course. And we have done the case study of a passenger car, and we have begun and done a case study of a passenger train. So, we stopped midway in the case study of a passenger train, and which is what we will continue further in this particular lecture. Okay, so common noise sources are these, and one by one we will discuss about a road vehicle, the railway and the HVAC. This is something which we will not discuss. And so, let us continue the case study of passenger train. So, we have already seen the various sources of noise in a passenger train. First of all, it is the engine noise, then we had the aerodynamic noise, and also now we will discuss about, so we had the engine noise, the wheel rail interaction noise is also very important, and after the wheel rail interaction noise we have this aerodynamic noise as well. So, today we will discuss in detail about the noise due to chassis vibrations. So, obviously the source of the chassis vibration noise is the vibration of the chassis of the train. Okay. So, this vibrational energy from the various moving components within the train, it could be either from the moving components of the engine, the rolling stock, the wheel rail contact, the braking system and various other components that is operating during the train run, and because of its operation the components are vibrating, and this vibration then slowly progresses in the structure borne way and passes into the main frame or the chassis of the train. So, they are mainly structure borne noise. They travel through the supporting structures of the source to the chassis, causing various connected structure to vibrate and radiate the noise. Even the body panels and the structural components, they also start radiating noise. We have seen that how in the machineries, when we have large panels, beyond the coincidence frequency, whenever they are excited, the structural vibration will then be converted into the longitudinal waves. Okay? So, these panels become a major noise source beyond the coincidence frequency, and they start radiating noise into the surrounding air, and then this noise can reach not only the surrounding air, which is if this is your train, the noise can reach into the outside atmosphere and the nearby people to the railway track. It can also transmit into the cabin and disturb the passengers and the drivers. And many a times when the vibrations due to the engine component or the rolling stock, the vibrations due to the wheel rail contact, the braking system or the pantographs, okay, the vibration of various of these components, if suppose they have a frequency which matches with the frequency of the frame of the train, then the frame will be set into resonance. So, when the excitation, so when the vibrations, the frequency of vibrations of these components match with the frequency of the structure, so here the chassis acts as the pathway for vibration transmission. So, when the vibration corresponds to the chassis natural frequency, then resonance is set, and in that case the vibrations of the chassis amplify further, and hence a very large level of noise is produced. What are the characteristics of this chassis vibration noise? The noise is characterized as structure borne noise, so obviously because it is the noise that is transmitting in the form of the vibrations in the chassis. So, here the chassis itself is not the source. The source originally was these various components of the engines, all these various components of the train, and then because they were working, they started vibrating, and this vibration then transmits and flows into the entire train by passing through the chassis. So, it is a structure borne noise. It travels throughout the train body, and as already discussed in the previous module when we were discussing about the differences between an airborne noise and a structure borne noise. Typically, the structure borne noise is more low frequency content, whereas airborne can be low to high, all audible frequency ranges are covered in the airborne noise. So, because most of the mechanical structures, because of the dimensions that they have, their natural frequencies are always in the lower range. So, whenever the sound is passing through in the form of vibrations through these structures, the lower frequencies, they are amplified and the higher frequencies are not. So, the chassis vibration being structure borne has low to mid frequency content within this typical range of 20 to 1000 hertz. The vibration from the heavy components such as the engine, the wheels, etc., they generate noise in a very wide frequency range. But because the structural resonance corresponds to lower ranges, so the noises at the lower frequencies get amplified, so the overall chassis vibration gets higher low to mid frequency content. What is the impact of this? Obviously these vibrations, so first of all, this noise is propagating through the chassis or the frame in the form of vibrations, and whenever the vibrations they are exceeding the coincidence frequency, then these vibrations they radiate into the air. So here the impact is twofold. Obviously the vibrations that are there will cause discomfort due to the low frequency content in that vibration and just the sense of vibrations. Obviously, if you are sitting in not a very well designed or an old model train and you see the vibrate when you touch the chassis or when you touch just the body of the train while it is moving, you can feel the vibrations. Okay? So, whenever you touch it, you feel the vibrations and it is not a pleasant feeling. The long term exposure to these vibrations in our body can have negative effect. It can cause fatigue, it can cause various kind of sensory motory disorders as well. So, it is not a very pleasant effect, it causes discomfort to the passengers the more vibrations they are, and once these vibrations propagate as noise, it causes discomfort through the noise level as well. So, what are the strategies for mitigating these chassis vibrational noise? First of all, obviously because it is a structure borne noise which is passing as in the form of vibrations, so you would like to attenuate this. So, you can do it using the standard techniques of vibration isolation. So, isolation mounts could be there, which means that all these sources such as the rolling stock, the pantograph, the engine, the wheel rail contacting, the braking system, all these original sources, they should be connected to the chassis via some mounting. Okay, so the mounts or the systems or the structures that are connecting these sources to the chassis, they should be more vibration resilient so that they can stop the vibration to pass into the chassis. So, isolation mounts such as the rubber or the spring mount between the heavy vibration source. So, whatever is your vibration source, be it the engine, the rolling stock, etc., and then this is your chassis system. So, between them the mounting system that is there which is used to mount this source to the chassis, it has to be either vibration resilient, it should be able to stop the vibration. So, it should be more like vibration resilient mounting or use of isolators in between in these structures, so that the vibration does not pass through from the source to the chassis. Then the structural reinforcement and design can be done for the chassis itself. So, the chassis could have more better design of the chassis, which means that you can have some reinforcement panels such as adding the ribs or the additional support to the structure. It can reduce the tendency to resonate, so that even if the vibrations are passing, so the first thing is to stop the vibrations from passing from the source to the chassis. You can do it using isolation mounts or using more vibration resilient mounting. And the other could be the chassis itself could be made sturdy enough so that even whatever vibrations that are passing into it, they are not easily set into resonance. Then various kind of advanced suspension systems can be found between the chassis and the passenger cabin. The noise control methods for a passenger train. So far we discussed source by source what are the individual noise mitigation strategies that can be used. Now let us see a summary of the overall passenger train and the noise control methods which are usually implemented in this. So first of all, because at mid or higher speeds, the most dominant noise is the wheel rail interaction noise. It could be either through the rolling noise or the road or the rail inputs and rail irregularities, and so whatever is, so the track and the wheel needs to be designed properly to control this very dominant noise. So rail grinding will smoothen out the irregularities on the track surface. It will reduce the noise generated by the wheel rail interaction. Then the wheel tread optimization can be done once again in order to reduce the noise due to the wheel rail interaction. So you can have smoother tracks and a smoother wheel tread design, so that when the two surfaces they are coming into contact, the frictional noise can be reduced, the rolling noise can be reduced. Then the track isolation can be done, which means that wherever the two tracks are being joined together, they are suddenly in these joints or discontinuities we have a heavy vibration. So what you can do is install the shock absorbers at these joints or various kind of sound absorbing materials between the rails and the ballast, and all of this is going to once again reduce the impact due to the wheel rail interaction. Then to control the aerodynamic noise, obviously the train outer body design plays an important role. So just like track and wheel design is used to reduce the various components of wheel rail interaction noise, if suppose the train's outer body is designed properly, first of all the aerodynamic noise can be controlled by using more streamlined design. So instead of having a train engine like this, we can have more streamlined design like this, which can, so where there is no abrupt change in the airflow over the train's body. Okay, it is not offering any abrupt changes to the airflow, and turbulence is being reduced and the aerodynamic noise is coming down. Then sound insulation, obviously insulating the outer body with absorbing materials such as foam, the composites, the acoustic panels, etc. All of this is going to reduce the transmission of the aerodynamic noise and the wheel rail interaction noise inside the passenger cabin. So whatever noise is being generated here, so let us say this is the noise generated by the wheel rail interaction, the noise generated by the aerodynamics, it should be stopped from going inside into the passenger cabin if you install proper sound insulation of the outer body. Then vibration dampening specialized rubber mounts could be used, shock absorbers, resilient supports, all of this will minimize the vibrations of the chassis and other components. Then cabin design, even inside the cabin in most of the modern trains, what you find is that there's lot of carpeting, lot of padding, lot of absorbers being used. Okay, so you have the hard surfaces. So what we do is that because the train cabin becomes a closed indoor space, so it has a reflective or a reverberant environment. The acoustic field is reverberant in nature. So in a reverberant field, the noise gets amplified because of the multiple paths it covers and reflections that happen because of it. So we can bring down the noise level in this reverberant space of a cabin by reducing the reflections, and for that we can have many kind of sound absorbers present inside the cabin. It could be in the form of like acoustic panels, the carpeting, the various kind of padded seats, etc., and the ceiling tiles, all of this, so that the inside reverberant space is such that it has a lot of absorbing surfaces and the reflections are minimized. Then the cabin design, so just like in the cabin design we can have various kind of absorptive surfaces inside, we can also have double glazed windows. So these double or triple glazed soundproofing windows, they further prevent the transmission of the outside aerodynamic and the outside wheel rail noise from entering into the cabin. Then sealed doors and windows, all these windows and doors should be tightly sealed, and weather stripping could be done so that there is no leakage, because even if you install you have a lot of insulation, even if you have a good insulating cabin or a lot of absorbing materials, but if there are lot of air gaps, there would be leakage. Even if you have a very good cabin design, but because of the lot of these leakages or the lot of air gaps present, the noise is going to come inside. It is going to be not very effective, the levels will still be very high. So, a proper sealing could be done and these acoustic leakages could be minimized. Then there are various advanced technologies that are also coming up. So, as already told you, the most dominant noise source is the wheel rail interaction noise, and it could be in the form of, it could be just due to the rolling phenomenon and the friction between the wheel and the rail and the inputs, the vibrational inputs of the rail going into the wheel and the axle system. So, one thing would be done is that we could have some different technology to propel the train so that the wheel rail interaction noise could be avoided at best. And one of these technologies could be the maglev technology, which is coming up. This is the new form of train propulsion technology where the train propels using the electromagnetic induction. So, a lot of the tracks, they have electromagnets, and because of the attraction and the repulsion between the rails electromagnet and the track's electromagnet, the train pushes forward. So, what happens here is that the train is never in contact with the, there is no wheels in the train and there are no railway tracks. So, this is the typical kind of a schematic, and the contact, there is no direct contact between the train and the track. The train is slightly suspended upwards or it is levitating, and because of that the frictional noises, the rolling noises, all of this could be avoided because of the new propulsion technology. Then some other advanced technologies such as hybrid and electric train power, this would help in reducing the engine noise because diesel engines, they are much more noisier in operation, but if you replace them with quieter electrical powered trains, then obviously the noise level due to engine goes down, particularly at the low speeds, because at low speeds the engine noise is dominant, and as the speed takes a certain value, the wheel rail interaction noise then becomes dominant. For all these methods, the maintenance and the management is very important. At the end of the day, it is a mechanical system, and the rule of the thumb is that when a system, any kind of mechanical system is operating, and if you can reduce the amount of resistance to its smooth functioning, you are going to bring down the noise level. So, basically the machine should be in a proper condition and should be able to function smoothly. The more it is further away from the ideal design and further away from a smooth functioning, and there are more sort of faults in the machine, then the noise level is going to go up. So, regular maintenance and management is a key for almost every mechanical system. So, even for a passenger train, the maintenance and the management is very important. Then smart condition monitoring can be implemented, where you can make use of the deep learning techniques or other kind of artificial intelligence techniques, and you can on board monitor the vibration levels or the electrical signals. So, on board you can have the sensors to sort of collect the vibrational data, the electrical data and the acoustics data on the board while the train is running, and based on the signature profile you can make a prediction that okay, this part is working well or this part has failed and so component may need replacement. So, this will not only ensure that the train works smoothly, but it will also ensure that the noise levels remain at check. Then the regular maintenance and the lubrication among the various contacting surfaces is always important. So, with this I hope you enjoyed this lecture. Thank you for listening.